All right, so this first one, we're comparing these two graphs. If you notice, if you subtracted 4 from the y, it would give you the -2 like it's on the right side of the equation. If you added 2 to that -1, it'd give you the +1 that's next to that other x. So we know it's a vertical shift down. That's a little red for. And it's a shift to the right by left. Now, why is it a shift to the right? Because it's a +2. It's a shift left, and you might be thinking right, actually. So if we look at the graphs, I can like convince you here, at least graphically. Look, the blue is to the left of the one on that's red. So it's really like when you add two, but it's really next to x. It's like it acts opposite in a way that you would expect. So that's the best way I can like kind of explain that. The other one, we're looking for holes. Holes are when you divide by 0. Vertical asymptotes can be that too when you divide by 0. So we're going to want to distinguish between those. Factor the bottom. And I'm guessing and checking factors. I know it's 5 and 2 to get 10. Oh, and 5 and 2 subtract to get 3. But it's a -10, so one of them has to be negative. You could just guess and check those factors, but I know it's got to be a +5 and a -2 because I want to get a +3. So we're dividing by 0 when x equals -5 and x equals +2, but these don't cancel out, so that means they're vertical asymptotes. If they did cancel out, they would be holes. So both of these are vertical asymptotes. For all of these, I want to check them graphically, but I'm not. Notice how I didn't rely on doing the graphs to get them. This is just confirming that, yeah, look, those are vertical asymptotes. They're little dotted lines, and so the graph never wants to touch them. You can do this all without even graphing them. Graphing is just a way to check and help, but you can do it faster by factoring it. And here, if you see I write the factored form, you see how like it highlights right over the previous one. We have vertical asymptotes, and the equations don't just write the number, write x equals, and then where that happens. Again, we get that number. The reason they switch sign is because we're solving for when they equal 0. Okay, let's look at the holes or asymptotes in the next one. Now, first thing I see is that nicely this thing's already factored for us. That's convenient. All right, and we have a denominator is equal to 0 when x equals -2 or when x equals +3. So we know that the x equals -2 cancels out. So that one's going to be a hole, but the x equals 3, or the which is caused by the factor x minus 3 equals 0, that one doesn't cancel. So when they don't cancel, it's going to cause a vertical asymptote. It's going to cause that line that the graph doesn't want to touch. Again, I'm confirming it graphically, even though I did it algebraically. It's really hard to find the hole sometimes. Oh, there it is. I barely am able to get over it, but you can't find the hole on your calculator. You can only maybe guess it, but never rely on your calculator to find the holes. Just rely on factoring. Okay, next one. We want to factor the denominator. I'm going to assume that the factor at the top is a factor of the denominator because it would be really nice if something canceled, and often these problems do. So I'm just going to assume x minus 1 is a factor. So the other factor in there is also x minus 1. So is this a hole or is it asymptote? Well, it seems like it could be both because, well, the x equals 1 cancels, but then the x equals 1 is still there. So I'm going to graph it. And notice how it's an asymptote, and the reason is because if it's both, the asymptote will kind of dominate. So you can help check that with graphing. This one, same thing. When is your denominator 0? When your denominator is 0, that either causes a hole or an asymptote. Set the denominator equal to 0. This one doesn't cancel. There's no x plus 2 in the top, so it's got to be a vertical asymptote. Again, you can see it like just follows that. So that one's really easy. And there's nothing more to do here. Notice how I'm not doing the horizontal asymptotes yet. I'm going to come back to the horizontal asymptotes in later after we talk about 17, 18, and 19. So these right here, all I'm doing is sketching this. I notice that there's a negative. That flips it, instead of it first and third quadrant, it's the second, fourth quadrant. And so we know that this thing doesn't want to touch x equals 0. And so your domain, you can't put 0 in there, so it's all reals except 0. And the range is, you'll notice that it doesn't want to touch 0 on it doesn't want to touch the y-axis or x-axis. So the range is also everything except 0. This one here, same thing. What your domain is like the numbers you can put in for x. So we can put anything except, in this case, -3, because -3 makes the denominator 0. If you divide by 0, that just breaks math. Now, what about the range? Well, normally the range would be anything except 0, but see how this thing is shifted down by 4? Normal reciprocal functions don't touch the x-axis, but this one's shifted 4 down. So instead of the range being anything except 0, it's anything except -4. Now I'm writing that in the shortcut notation at the top. and I'm writing it in the infinity interval notation with the unions at the bottom. You can do, if you prefer to just to do y is not equal to -4, if you find that easier to write, go for that. Now I'm going to sketch this. Now the best way to sketch this is to put your asymptotes first, like right there, it's the vertical, horizontal. Then do the graphs. I just did the graphs and then I drew the asymptotes second. But it's kind of better to do in the reverse order. The next one, I'm actually going to do it in that reverse order, just because it's a little easier to sketch. But I just confirm that I'm graphing it right on Desmos. You can confirm it on your calculator too. It's just easier to type stuff into Desmos, just so I can do this quicker. Also, pretty colors. So now I'm going to go back and notice how I'm writing these horizontal asymptotes. All the horizontal asymptotes are usually y equals 0, but that's only when your top power is less than your bottom power. But notice how the powers tie here. Since the powers are in a tie, it's going to be whatever the coefficient of the top is over whatever the coefficient of the bottom is. So that one's y equals 5, whereas all the other ones were y equals 0. So that's going to be important later when we come to later when we want to get an asymptote that's not just y equals 0. This one, again, we want to find the domain and range. Always helps to factor this stuff. You can see how I'm factoring out the 2. It's like dividing by 2. The x plus 3 factor cancels out. And so this thing acts like it's just the function x minus 3 over 2, but the only difference is it has a hole at x equals -3, because if you plug -3, you divide by 0, and dividing by 0 is bad. Now, to figure out the range, it's a little hard, but I know that I can't put -3 into this function, but if I did put -3 into this function, it would output a value of, coincidentally, -3, so your range can't be -3 either. Again, if you want to see exactly what that graph looks like, since it behaves like a linear function with a pinhole, I'm actually writing it in slope-intercept form here. And again, we can use technology to graph this stuff, so this is like not a necessary step for like our current technology, but you could do this by hand if you needed to, except you'd have a pinhole here. The one thing your technology can't do, it's hard to find the pinhole. Look how long it is. Look how hard it is for me to find that pinhole at -3. Finally, I find it, right? It takes a lot of like moving around. My mouse is like too sensitive. Next one, same thing. If you can, always factor these. The bottom, it's not obvious to you at first maybe, but you can factor the bottom by factoring out a GCF of x. Then that's a perfect square binomial. I factor that thing. And you can't divide by 0, so 1 and -1 are both bad numbers. So 1 and -1 are not in the domain. Now the range is a little harder on one like this. It's like, wait, so do I do what I did last time? Do I plug -1 and 1 into the new modified function, and that's how I get my range? But actually, your range is actually, see that thing in the center? Your range will actually go through all real numbers. Even though it has horizontal asymptotes, it flatlines on the left and right end, your range is actually all reals. So sometimes the range is not always obvious. Domain's easy. Range like kind of just takes some practice with. The next one, again, we just want to do the domain and range. We know you can't divide by 0. If you put a 3 into x, it makes you divide by 0. I accidentally wrote a -3 right here. I'm going to fix that in a second. But this is the interval notation. Again, you don't have to write that long interval notation. Usually, maybe when you get to college, you might have a professor that makes you write that second one because they're just really particular about it. But we get what you say when you mean it's anything but -3, or it should be anything but 3 in this case. Now, your horizontal asymptote, just like before, since the powers on the top and the powers on the bottom are the same, it flatlines at 1. It then doesn't flatline at 0. The only time your horizontal asymptote is 0 is if your power on the top is less than the power on the bottom. But here, since they tie, they're both linear functions on top, linear function on the bottom, x to the power of 1 on top and on the bottom. It flatlines at the quotient of the coefficients. It's 1 divided by 1. 1 divided by 1 is 1. So that's why it has a horizontal asymptote there. Now I'm going to go back and fix those -3s. I had a bunch of -3s. Those should all be +3s. So I'm going to re-sketch my function here. Notice how I sketch the asymptotes. And once you sketch the asymptotes first, it's easier to sketch the function. So that's a good little tip if you have to sketch that. It's really the whole reason we find those asymptotes algebraically. All right, this one, what makes us divide by 0? Well, when x is 2, because 2 minus 2 is 0, so I don't want to divide by 0, so don't do that. All right, so the domain is all reals except +2. You can write it in that long union interval notation, but that's really just saying, hey, 2 is the only thing it's not. It's literally any other number. I want to find my range. I simplify that function. I notice that if I plug in 2 into the function, which I'm going to use function notation, if f of 2 is equal to, in this case, 2, coincidentally, the range also happens to be any number but 2. If you want, I can show you one where the range is something different. just so you know that it's not always your domain is not what your range is. Okay, again, so we can sketch that function, and like the best way to sketch it, if you're doing it by hand, is to, if there are any horizontal asymptotes or whatever, you sketch those first. But when this thing cancels, it cancels just a simple linear function. It's just a line with a slope of 1, y-intercept of 0. And you can see I can find that pinhole by barely hovering over it, but you'll never, ever, ever see the pinhole unless you're like right exactly at that point. So I'm gonna exaggerate the pinhole in the sketch, even though the pinhole is really small. We draw those giant holes. They're not really that big, infinitesimally small. All right, this one, these are open-ended. There's more than one answer to these, but this one's easy. Vertical asymptote at x equals 0. That means x equals 8. That means we divide by 0 when x is 8. So x minus 8 is your denominator. And then it's just 1 over x minus 8 because you want your horizontal asymptote to be y equals 0. All right, next one, you want a vertical asymptote at x equals -4. So x plus 4 is your denominator. So we make that the denominator. But here's the problem. How do we get a horizontal asymptote that's not just y equals 0? See how I'm off here? Like I try to mess with the numerator. No, it doesn't work. Well, here's the thing. You got to remember that your top power and your bottom power have to tie to get a horizontal asymptote of just a number. So 3 over 1. So that means instead of just having 3 or something in the numerator, you put 3x in the numerator. So x is the first power in the top, x is the first power in the bottom. They tie. The coefficient of that x is 1. 3 over 1 is 3. Now, notice how it just works. And now you have a horizontal asymptote of y equals 3. So that's how you do that. I'm going to also show you another one. Look, see how if I make it 3x squared over x squared plus 4x, that also has a horizontal asymptote too. That's why it's an open-ended question. It's more than one answer. All right, next one. Again, we want a whole. That means we have to have the factor that you divide by 0 in also exists in the top. That way it's not a vertical asymptote. It cancels out. We do want a vertical asymptote when x equals 2. So x minus 2 is a factor there. So I'm going to put this into decimals just to confirm that it does exactly what we want, and it does that. So we got the whole where we want. Now I'm going to find the whole in the table. It's just a little easier to do. So if I plug in -5 into the table, notice how it gives me a value of undefined, and we can see there's no asymptote there. All right, this one, how many inverse variation functions have 2, 3 as a solution? X is 2 and y is 3. I would think, well, maybe infinitely many, right? But the thing is, you got to remember, inverse variation functions, you're not able to shift it up, down, left, or right. So the only function is y equals 6 over x. Well, we can rearrange the y and the x and the 6. For instance, couldn't we do x equals 6 over y? Or couldn't we do x times y equals 6? But each one of those, x equals 6 over y and x times y equals 6, they are all the same function. So it's really, the answer is really just 1. All right, starting to wrap up. The next one is still an inverse function, right? Those kind of reciprocal functions. We're given an a and a b. Now this is a very it's variable strong on this question because they're saying give 3 of the points, but they didn't give us the numbers a and b. So, but notice that if you doubled a, you would half b. If you multiplied a by 5, you would divide b by 5. I'll show you an actual example where this can make a lot more sense to you. I'll just show you a little table and chart of a real reciprocal function. So if you have no idea what I'm writing here, just watch what I'm going to do. Let me take the easiest reciprocal function I can think of. Y equals 2 over x. And then what we'll do is we'll do a little example of showing you that when I double the x, you'll notice that it chops the y in half. If I double the y, it should chop the x in half. But we can do all these, like if you notice I'm doing the algebra here. If you double one, what you're ending up doing is halving the other. If you quadruple one, you divide by 4 the other. So let's just take this, put it in a table, and I'm going to not use these values right here, but focus on the 1 and the 2. When I double the x, notice how it cuts the y in half. Now I'm going to double that x value of 2 to 4. It cuts the y in half again. If I half the x values, it doubles the y value. So you can see that summarized in this chart right here. And when you double one, you half the other. Last one, we want to graph these two equations, and we want to compare whether they are the same graph. They are almost exactly the same graph. Here's the only difference. When you factor it, that thing cancels. That's going to be a tiny pinhole. The only difference between the first function and the second one is that the first one has a little pinhole at x equals 2. They both have an asymptote at x equals 3, but the second one just has that little pinhole. Otherwise, they are identical as far as the eye can see, but there is that tiny pinhole, so there's practically no difference. They are basically equivalent, except for an infinitely small amount of area. All right, that's it for this one.